most of the lesson. We'll finish it here. All right, which means that you probably want to be thinking about the next assignment, but I will give you a work period Monday. Something a little different. There's no quiz with this lesson. There's no quiz, okay? It's almost like I want the assignment to sort of serve as the quiz. So, as you should always do, focus on the assignment, but that I'll end up grading like most of the problems. Trying to encourage you guys to do a nice job with it. Actually, want to look at another problem in the book. It's in the same section, but it's number 24. Number 24. It's on page 131. Because these are word problems, it is easier just to see the words. Take a look at it. It's up to you if you want to redraw the sketch. Again, I'm just putting it on the board so I can actually point at some things. One of the reasons I want to go over this problem is to kind of say this, especially to my friends that already took physics, that you try not to say, oh, I don't remember this, or oh, I kind of remember. Actually, might be better. It would depend, but it might be better if you don't remember it, because I'm going to try to give you a method. Now, it could be the same method, but it might not be. But it's kind of like the calculus method. Okay, now this is a position graph, and even though that's kind of a physics idea, it's a position graph. If you look at question A is really a slope question. Okay, so my suggestion to you here is let's all be like the slope student. Let's look at this with slope glasses. It's supposed to be the sort of the right way. It's supposed to be the connection way. Okay, so this is a position graph, but question A is really a question about slope, because when you're moving to the left, you're supposed to have negative velocity, which means negative slope. When you're moving to the right, you're supposed to have positive velocity, which of course means positive slope. Do you realize here that I'm using the word slope kind of synonymous with velocity, okay? Because of course they are the same. And when you're not moving, you have zero slope. Okay, so it's all about the slope, the slope, the slope. Okay, I'm sure it doesn't surprise you to hear me say that that is a section of positive slope. You know that. But because that's positive slope, that means that it's positive velocity. And so we can say that by just saying that you're between 0 and 1. You're between 0 and 1. Now, technically, when you're at 1, you're at a corner point. And since it's a corner point, we should have learned in the last section that there actually is no slope there. So I guess technically we can erase the equal to. Okay, there's no more positive slope on the board, but we do have some negative slopes. And so, again, I'm sure it doesn't surprise you for me to say that that's negative slope and that's negative slope. Okay, but negative slope means negative velocity. Just need to say so. So that's between 2 and 3, and it's also between 5 and 6. I'm writing the answer with inequality signs. You could write the answer with interval notation if you want to. Now remember, if this was the lab where there's a motion detector going tick, 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 you're going to be walking towards the motion detector for a second. Then you're going to stand still because your position's not going to change. And since your position's not going to change, and since you're standing still, obviously you have zero slope. Okay, and then I'm going to walk backwards, tick, 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 and then I'm going to stand still. And I'm going to walk backwards a little more. But let's say we're at zero. It's zero between 1 and 2, and between 3 and 5. Now the idea there was that was all based on the slope, the slope, the slope. Okay, because again, the slope is the same as the velocity. Now here's the next neat thing, and it's basically question B, but we got to do something to get question B figured out. It says to graph the velocity. And again, sometimes kids are like, oh yeah, I remember that. You had to graph this graph, and then you had to graph this graph. Lots of fun, right? All we got to do here, though, is think about the slope of these lines. Okay, because the slope of this line is actually the velocity of the line. And it looks like that it goes up to 2. So I could say that the rise is 2, the rise is 2, and the run is 1. So this one has a slope of 2. Okay, but what that really means is I have a velocity of 2 meters per second. How about the slope of this line? And you see what I'm doing here? It's just a rise over run. So if I rise -4, is that what it would be? If I rise -4 and run 1, I get an actual slope of -4, which represents a velocity of -4. And then I can do a little rise over run on this one. It looks like you're going to rise -2 and run 1. Okay, and then the slopes here are pretty easy. The slopes are 0. Now, these circled numbers, they represent the velocities because the velocity is the same as the slope. So when it comes time to graph my velocity or to create my velocity graph, I'm just going to be graphing these slopes. What do you mean graphing these slopes? Well, if I'm going to graph 2 for 1 second, then I'm going to draw a line at 2. If I'm going to graph 0 for, oh, do I have a little typo here? No, 1. So if I'm going to graph 0, I'm using the same color, but I'm drawing a line at 0. And then I'm going to graph -4, so I'm drawing a line at -4. And then I'm going to graph 0. Again, it's the same color. And then I'm going to graph -2. When you graph these, you're actually just drawing a line at each of these y values. Okay, they don't connect. They don't connect because the slopes don't exist at each of those transition points. Okay, so my velocity graph is just lines that represent each of these slopes. When you look at a graph, I want you to wear your slope glasses. I want you to see slope because slope of the position graph is velocity. Okay, and again, this graph over here really is the graph of each of those velocities. Now, there's one more thing I want to do with you, and it's neat. It's actually something I don't think I ever quite understood in high school. That's not an excuse for you guys, but I'm just being honest. It's kind of trying to understand beyond like the velocity acceleration concept, a little bit beyond physics. Now, agree with me, I hope, that a derivative is a slope. Okay, that's a key idea. Derivative is a slope. From your basic ideas about slopes, slopes are also rates. So derivatives are rates. Okay, they don't have to be velocity rates. They can be a rate based on anything that is being consumed. Okay, so just go with this with me for a second. Population. If I have a formula, if I have a function for population, Okay, like, the population of a certain area in a certain year, and then for another year. So it's a formula that gives you the consumption of population. Consumption just means like the total. If you do the derivative of that, well, now you're going to have a population rate. You're going to have the way that the population is growing. You see, as soon as you do a derivative, you turn like a consumption equation into a rate equation. It wouldn't have to just be for population. It could be for anything that talks about like a total amount of liquid. If you're filling something up, like the bathtub. Now, if you're filling up the bathtub, how much water is in there after 1 minute, 2 minutes, 3 minutes? Okay, it's some certain volume. As soon as you do the derivative, this is the neat part. As soon as you do the derivative of volume, you're going to get a volume rate. You're going to get how fast the water's coming out of the spigot. Okay, now it might change. It might not change. It depends on what factors. Derivatives give you rates, and they can give you a rate of any consumption. Back to the position, velocity, acceleration. You are consuming distances. If I travel a certain distance, that's my S equation. But as soon as I do the derivative of S, it turns into a rate. It's the rate of that distance. We know that as velocity. Okay, and it's the same thing here. Well, there's an application, it's the last one we're going to do, that has to do with money. Money. Okay, by the way, some of you, if you go to college and take like a business, degree, get a business degree, you'll probably take calculus, but it'll be what's called business calculus. And basically business calculus, every application has to do with money and other things with business. But so you won't do like the physics applications, you'll just do this type. Cost equation. Okay, it costs so much money to make so many widgets. If I make 100 widgets, it costs so much money. If I make 1,000 widgets, so I have a cost equation. If I do the derivative of cost, it gives me the rate. Now, the cost rate is known as a marginal. And I'm just going to kind of be honest with you here. I didn't study this like when I went through college because I did like the physics application, but I can still try to help us understand this. If you do the derivative, you get what's known as a marginal. A marginal is the derivative of the cost function, and in loose terms, it means the cost of producing one more. Okay, if I make 100, what's it going to cost if I make the 101st widget? That would be known as the marginal. Basically, it would be the derivative cost. Okay, and again, that's kind of in loose terms. And I'm just being honest with you, I never really studied that in a lot of detail. And so there's still a little bit of that I'm kind of like, what exactly does that mean? And we'll do that with a word problem, so we at least have some numbers that we can look at. Now, if you look in the book, I like using the book. You guys, if you go to college, you still might buy some books, so you want to use them. And I'm going to draw your attention to page 128. We're going back to page 128. There's a little paragraph. I encourage you to read it. It starts with engineers. And you can probably stop when you get down past the third paragraph. Past the third paragraph. Okay, so it was just another way to listen to what I was attempting to explain to you. Again, different types of rates, in this case with money. Let's do example 6. Okay, example 6 on the next page gives you a cost equation. Now, it's up to you if you want to write it down. It's already there. But we have a cost equation. For some reason, depending on how much X you make, I guess they're radiators, it's going to fit into that formula. And then you'll see that there's also a revenue equation. Now, if some of these money terms are throwing you off, revenue is then how much money I'm making. But that's different than the profit. Okay, revenue is just how much money, I guess, when you sell the items, how much you make when you sell them. Of course, the profit would be the difference between these two. But in any case, if you look at the question, it basically says find the marginal cost and the marginal revenue, okay, for 10 radiators. And we can find that if we just understand that the marginal is going to be the derivative. So when I do the derivative of the cost equation, well, it's not a real hard derivative to do, but I basically get like a rate equation. And so when I plug in 10, and again, you can see the book did it, but when you plug in 10, you end up with 195. In loose terms, and I kind of wish I even understood this a little bit better, but in loose terms, that means that the cost to make the next radiator, like the 11th radiator, is going to be 195 bucks. Okay, and for some reason it changes. It changes probably because it depends on how many you make, as to how efficient you are and all that. But the marginal cost for 10 radiators is 195, which means that to make the next one, it would cost you 195. And then the revenue, kind of the same idea. You can do the derivative. Okay, pretty easy derivative, just change the exponents. But I can find the marginal revenue, which again, you can see that they plugged in 10, and apparently out pops 252. $252 would be the revenue that you would make if you sold the 11th radiator, if you sold the next one. There probably will be some of you, one of you, someone that studies some business calculus, and you'll talk much more deeper about marginals. Come back and talk to me about it. Okay, I'd like to know a little bit more, but it is the economic derivative. It's the economic application. Okay, on Monday, we'll give you that work period. I actually have a little bonus problem that I'll give you at the beginning of the period Monday. But instead of squeezing it in today, I think it'd just be better to do it Monday. Okay, if you want to start your assignment, never a bad idea. And then that assignment is due Tuesday.